Hello, people, and welcome back to another session. In this session, we'll be discussing two-way analysis of variance and interaction. So, we have already discussed one-way analysis of variance. In one-way analysis of variance, if you remember, our objective was to find out whether the groups which are present in our sample are distinct or not based on a specific parameter. So, in one-way ANOVA, you had one factor variable and you had one parameter or numerical parameter, however you like to call it. So in two-way analysis of variance, how is it different from one-way ANOVA? That rather than having one factor, now you have two factors. So in two-way ANOVA, you have two factors, but you still have one parameter based on which you need to find out distinction amongst groups. Now, taking on from our discussion of hypothesis testing, if you remember, the global F test for my one-way ANOVA was to find out whether at least two groups out of the k groups present are different or not. We are still not bothered about what groups are different. We are only bothered about which of the two groups are different, right? So here in two-way ANOVA, what we are trying to figure out through our global F test is which factor has an impact on our group distinction. Which factor actually has an impact on distinguishing the groups, whether it is factor 1 or factor 2 or both. We still don't know exactly, but our goal is to figure out which factor has an impact. And how do we do that? We do that by taking one factor at a time, keeping the other factor constant. So if you can see, this is a sample example where I have factor A and factor B. The values of factor B extend from 1 all the way till C, and for factor 8 ranges from 1 all the way till R. Assume we are trying to figure out the impact of drugs on male and female students. So in factor A, which will be gender, it will be male and female. And on factor B, it will be the two types of drugs we are trying to test, drug A and drug B. It is a sample extrapolation of this particular table to a real world example. But coming back to this table, if I only consider factor A, if I consider factor A, and I'm saying that I'm going to be keeping factor B constant throughout. Again, I'm going to be keeping factor B constant throughout, and I'm going to be measuring the effect of factor A. So because B is constant throughout, so this particular column is going to be the column for our analysis. So we are basically doing column wise analysis where we are stating our null hypothesis as mu1 dot is equal to mu2 dot is equal to mu3 dot all the way till mu k dot. And my alternate hypothesis is checking out whether any one is different from the other. This is basically my null and alternate hypotheses for testing the effect of factor A, keeping factor B constant. If I had to do the reverse, if I had to check the impact of factor B, keeping factor A constant, let us do that as well. So if I have to check for factor B and I'm keeping factor A as constant, so my null hypothesis will change accordingly. So this time my factor A remains constant and my factor B changes. It means this time the analysis is done row wise rather than doing it column wise. So it will be mu of dot 1 is equal to mu of dot 2 is equal to mu of dot 3, so on and so forth, all the way till mu of dot k. Alternate hypothesis will be mu of dot I mu of dot I is not equal to mu of dot j. So this is my null and alternative hypothesis for trying to test the impact of factor B. Now, before I do my two-way ANOVA, now if you remember when we were discussing about regression, we talked about regression diagnostics. And what was regression diagnostics? Regression diagnostics was a process of checking a few conditions, a few assumptions rather, that should hold true before I go ahead and I create my regression model. So certain assumptions need to be sacrosanct before I actually draw any conclusions from my regression model. In the same way, for my two-way ANOVA, there is a test called as an interaction test. The interaction test is done to check whether the factors involved in my two-way ANOVA, whether they interact with each other in any way. If there are significant interactions present, then any sort of conclusions that I draw from my two-way ANOVA are either false or misleading at best. So it is very important to check for interactions between my factor variables before I draw conclusions from two-way ANOVA. Now let us see how can we do that. Before I before I go over explaining what, how exactly can we check whether the two factor variables in our data set are interacting or not, I want to try and pontificate on what exactly is an interaction in case of a two-way ANOVA scenario. On a two-way ANOVA scenario. So basically, an interaction exists when there is no overall change in the marginal means, but there are variations within each factor. Only then we can surmise that there is an interaction present. Now take a similar example like this. If I say that there is factor A, there is factor B, something like this. Now, here let us suppose I keep gender. Here I keep drugs. There is male, there is female, there is A, and there is B. Let us suppose we have these four values, and let us suppose that for each of the mean values, let us suppose I have 10, I have 20, and let us suppose I have, what do I have? Let's say I have 25 and I have 5. So basically, marginal means are basically mean of all of, basically it's the mean where we keep one as constant and the other varies. So here for male, I will check the mean of the drugs. It will come out to be 15. For female, comes out to be 15. For drug B, if I for both male and female, if I do the average, it comes out to be somewhere around 12. And here also it comes somewhere around 12. So if you look at these marginal means, oh sorry, I'm wrong. I'm wrong over here. Let me correct this quickly. So 20 plus 5 is 25, by 2 is 12.5. This is 35. 35 by 2 is 17.5. So these two are not same, but this marginal mean is same. So we can say because the marginal mean of drugs varies, drugs has a significant effect on my parameter. Gender doesn't have that much. However, if there is a case where for the same situation, let us suppose there is male, there is female, there is drug A and there is drug B. 100, 300, 300, and 100. Now, what is the value of my marginal means? This will be 200, 200, 200, 200. So here, the marginal means for drug A keeping, uh, for male and female keeping drug A constant, for male and female keeping drug B constant is same. And same goes for gender, the gender scenario as well. When we keep gender constant and we vary the drugs. Because of these same marginal means, here we can conclude that there is an interaction. So the overall marginal means, when these do not change, only then we can say that the two factors in our analysis are interacting with one another. Now, even in case of interactions, there are two different kinds of interactions that are present. One is called the quantitative interaction and the other is called the qualitative interaction. Now, what are these two terms? Now, basically, when in this graph, if you see, we are trying to analyze the change in math scores for male and female students based on their age. And if you see for males and females, there are two graphs which are drawn here. So if you look at the scores and how they vary with the birthday month, for both male and female, we can see that as the birthday month increases, their scores have also gone up. So there is a direct relationship between the birthday month and the score for both the categories. Although the magnitude of change, that is something that is different for both. Only because the magnitude of change is different, but the change exists in the same direction. Therefore, we can say that here the measure of my interaction is quantitative, or the type of interaction is quantitative. On the other hand, if my scores are changing for females in a positive direction when it comes to my increase in birthday months, but in the opposite direction for males when we increase the birthday months, it means that the direction of change is different for both males and females. So when the direction of slope changes in an interaction plot, we can say that the type of interaction is qualitative in nature. So we test, or we basically see interactions through a plot called as an interaction plot. In the interaction plot, if for my two categories, if the quantity of my slope is different but the direction is the same, then it's a quantitative interaction. But if the direction also changes, then that interaction becomes a qualitative interaction. Now that we have looked at the theoretical aspect of it, let us go to R and do a sample R problem. I have a data set called exercise. I have taken it from GitHub. It looks something like this. There is a column called pre-stretch. There is a column called ankle weight. If you see, there are two categories in both: no stretch and stretch, and no weights and weights. So there are two factor variables and three parameters. Now I'll just go ahead and I'll attach my exercise and I'll start creating my models. So in the previous case, you saw how we would create an ANOVA model using regression. We would create it using my parameter, tilde, my factor variables. Okay. Here we do a similar thing. What we do is that energy, we will first create the model based on the energy parameter. So based on energy, we are trying to see whether there are differences between stretching, stretch and no stretch, or no weights and weights. So what we'll do is that we'll keep both my pre-stretch and ankle weight as my group, but we'll also check for interaction. And when we check for interaction, we basically also multiply the two, and then we create the model. So we create the model. And then the ANOVA gives you the result for your pre-stretch, ankle weight, and both pre-stretch and ankle weight. So if you see, the p-value of pre-stretch into ankle weight, or pre-stretch colon ankle weight, is exorbitantly high. It means that the significant factor in this equation is extremely high. Therefore, there is no interaction present between the two. Same for the next one, but this time we are considering oxygen as our parameter. Let us go ahead and use ANOVA. Again, you can see not so significant. For speed, again, you can see pre-stretch colon ankle weights, the value of p, or the p value, is exorbitantly high. It means that pre-stretch into ankle weight is not a significant factor in the model, and therefore we can conclude that this pre-stretch and ankle weight, these two factors do not interact with one another. Now we will come to interaction plots. This is how you create an interaction plot using interaction dot plot, and you give your two categorical variables and then your numerical variable. So if you look at all these three examples that I've shown you, you can see that the direction of the slope, is the same, whereas the magnitude is different. And therefore, the nature of interaction between them is only quantitative in nature. So this ends our session on interaction and two-way ANOVA. I'll see all of you all in the next session. Thank you.